hold. Okay, could you please start, Sebastian?
Yeah, Irina, thank you for the extensive introduction. So I probably have to update my LinkedIn profile a bit more. But yeah, so basically, yeah, since I think 3 or 4 years, I'm now at DESY and working at the Synchrotron. We're first I started working here as a beamline scientist at one of the macromolecular beamlines here, crystallography beamlines, and then I moved to Alchemins group, and here we are working on quite a lot of projects to develop methods for theory crystallography, but also other crystallography, mostly crystallography centered projects, but also beyond. So yeah, thank you for giving me the opportunity to talk to you about the work we do. Quite a lot of this work has been conducted at BioCars. Yeah, and with this, I guess I'll just get into my talk. So I will briefly start with a very short primer on to go back. So I will talk about fixed target pink beam theory crystallography to study protein dynamics. And so I will briefly go over the theory crystallography and why we use fixed targets for this, and then give a few examples of how we use the methods we developed to study protein dynamics. And then in the end, probably give a little outlook of what more method we do in terms of method development. Okay, very short primer on conventional versus theory crystallography. So with conventional crystallography, you typically have one or very few crystals. You take rotation images. Typical crystal size is around 100 by 100 by 100 cubic micrometers, but with new beamlines and beamline optics, this can be much smaller actually. Exposure time, total exposure time for crystal is usually around 10 to 100 seconds. The drawback of these rather large crystals, typically if you want to do some time result studies and you want to activate your protein with a light pump probe, or in general with some laser, you will have absorption effects, and so typically the light doesn't penetrate homogeneously through the whole crystal. On the other hand, if you want to induce some changes by soaking in the ligand to observe then subsequent changes in the structure, the diffusion time can be limiting because the larger the crystal, of course, the longer the diffusion will take. And so you will have reactions starting already on the surface of the crystal, while in the center of the crystal, this might not have started. So opposing side, you have theory crystallography, which was actually developed out of the need. If you want to do crystallography at X-ray free electron lasers, where you have a very bright, intense X-ray pulses, which basically obliterate your sample as soon as you look at it, but you can record the diffraction pattern before, so you can get some information of the state of the protein or the crystal before it was destroyed. So for this, you typically collect thousands to 100,000 of images, which are still images. That means for each image, you have a new crystal. Crystal sizes are much smaller than 10 micrometer, micrometer, maybe on the average of 5 by 5 by 5 square cubic micrometer. Exposure times per individual crystal can be from femtosecond at XFELs up to milliseconds at synchrotron sources. And due to the much smaller size of the crystals, usually have homogeneous light penetration, and also the diffusion times are much faster. Like I said, for the theory crystallography, typically you have a single crystal, and once it's hit by the X-ray pulse, you move to the next crystal. And for this, you need fast sample delivery systems. And over time, there are several which have emerged, mostly through development at XFELs, but also at synchrotrons. So we have liquid jets, where we have our crystals in a slurry, which are then jetted across the X-ray beam. We have LCP jets, lipidic cubic phase jets, which are more viscous jets, which can run at much slower speeds. So this is something that can be conveniently done, also used at synchrotron sources. Then you have fixed targets where you deposit your crystals on a fixed target, for example, a silicon chip or nylon chip, and then you scan this chip through the X-rays. And there are also tape-based methods where you have a tape which is pulled across the X-ray interaction region, and then you have your crystal slurry which is deposited on here. And we have focused our developments on fixed targets because these are usually the most easy to handle, have very low sample consumption, and have a rather low maintenance. So this is a very, I have to say, biased view on if you compare all the different sample delivery techniques. So if you have liquid jets, you can reach very fast sample exchange rate, and this is optimal, for example, for XFELs or, for example, at the European XFEL, where you have megahertz X-ray pulses arriving, and you need to have a new sample, fresh sample for each X-ray pulse. If the jet becomes very thin, you have also low background scattering. However, you have usually quite a high sample consumption, and they are widely used for pump probe experiments. LCP jets, sample exchange rate, it's, like I said, you can't flow them as fast as the liquid jets. Through the LCP material, you have usually quite a lot of background scattering, which of course is bad for your signal to noise. Sample consumption is much better. And with the large background scattering, usually you have some negative effects on the pump probe capability. Tape drive is somewhere in between. And the fixed targets, you can have intermediate, I would say, exchange rates. We have done this already at up to 1 kilohertz, which is not enough for the European XFEL, but we will get there, hopefully. And with the fixed targets, you can reach very low background levels, which I will show you in a second. Sample consumption is very good because you can basically, in theory, you can hit each crystal which you put on your fixed target. And as I show you, they can be easily used for pump probe experiments. So how would fixed target crystal zero crystallography experiment work? You take your crystals, you put them on one of these chip holders, you put this on the X-ray instrument, you define your scan parameters, you have a high speed scan of the chip through the X-rays. At the XFEL, this is then synchronized, for example, through the incoming pulses, and then we can just go on and analyze the data. Chip loading on a fixed target sample mount. This is shown for, in this case, this is a small silicon-based chip. We have, for example, if you have your crystals grown in a batch, you would deposit a few microliters on these small chips on the chip surface. Then you will use blotting paper, touch it from the bottom, all the liquid will suck through, and the crystals will remain on the other side. And then you can blot this, you can freeze it, for example, if you want to do cryocrystallography, which we, for example, can do at synchrotrons, or you use this at room temperature. Here you have to be careful that as soon as the crystals are removed the excess liquid, of course, the crystals can start to dry in. So you need to provide a humidified airstream. To further prevent the crystals from drying, we developed this sample holder. Here you have the, this is the standard magnetic base, which is used at typical macromolecular crystallography beamlines. There's a 3D printed sample holder, which is a reservoir. Here we have our silicon chip. And here you add the crystallization solution. So basically the buffer composition in which your crystals would be. And then we have a cover which we can slide over. There's a O-ring here which is sealing, which seals this airtight. And we have Mylar windows here. So now we have evaporation, and the air or the atmosphere around the crystals will reach the same level as the crystals had in the crystal slurry, so that prevents them from further drying in. Like I said, for synchrotrons, we typically use these very small chips, 1.5 times 1.5 square millimeters. But we also use larger, 4 by 10, or recently we switched to 6 times 16 square millimeter. This all depends a bit on what the goniometer at each beamline can handle. And for XFEI experiments, but also, for example, the biocars, we already use these large chips, which have an active area of 10 by 32 square millimeters. And you can fit hundreds of thousands of crystals on these. All right, something else to consider for these serial crystallography experiments is, of course, always your signal to noise. We can drive the signal, of course, with ever brighter and more intense X-ray sources like Max 4 or the APS. It's already pretty bright, but after the upgrade, this will even further improve. Which allows now requiring of very strong signal in rather short times. And this is, of course, well suited for time result studies, right? Where you want to look at probably processes which proceed on very femto pico or micro nanoseconds. And this is especially true at X-FELs, but also at pink beams, which I will show you at, for example, at biocars. On the other hand, of course, it's not only the intensity or the signal, but also the noise level, which we can manipulate, right? So, for example, if you have in-air experiments, usually you have a lot of scattering from the air, which can be alleviated by, for example, moving everything into vacuum, which has drawbacks by itself, of course, or you flush the interaction region with helium. You can make sure that your sample delivery technique provides by itself a rather low background, and you can look that you further reduce noise level of your biosample. So what are sources for background scattering in crystallography? This is a view of the interaction region on a macromolecular crystallography beamline. We have the beam coming from here. We have our sample here. Here the beam stop. So of course, the beamline components themselves will scatter, can contribute to background scattering. Then we have the sample, which can be disordered. The sample holder can contribute to scattering, and of course, all the liquid around it. And then we also have air scatter, where the direct beam, which pass through the crystal until it hits the beam stop. So for this, especially for this air scatter, we developed these capillary shields, where we have our sample here. This is, in this case, a chip. We have the X-ray beam coming here. This is a collimator coming from the on-axis microscope, so this part here. And then we have capillary shields directly behind the sample so that we can close this air gap. And this leads to rather low background levels on the diffraction on the images, which of course is very helpful if you have rather small and weakly diffracting crystals, which is in particular useful for pink beam experiments. So these are just some sample diffraction shots from biocars, where you see that at least on this representation, you see a rather flat image except for the diffraction spots. And of course, for time resolved studies, you want to excite your sample. And I will talk here about pump probe experiments where we excite this samples with the laser light. And for this, we also developed an on-axis microscope, which has the option to couple in the laser light so that you have a collinear excitation of the sample to laser. So in this case, we have our sample, which is moving back and forth. Here we have the detector. The X-rays coming here, and you would have, this is a fiber forward where you could couple in your laser light, which is then deflected over mirrors to be collinear with the sample. Okay, so I'm coming to the first experiment. One of the first experiments we did for pump probe experiments. This was done at biocars. So here we used photoactive yellow protein, one of the I guess guinea pig guinea pig crystals for crystallography, or time resolved crystallography. It's actually one of the first, was the sample of the first femtosecond crystallography study done at X-Fels. And we can see light-induced changes actually from the picosecond to milliseconds scale. And what we see is a transit isomerization within the chromophore. This is from from now already almost 10 years old paper about the photocycle. So at biocars, we have, I guess, this could be studied from the 100 picosecond scale onwards. Actually, from this publication, this is suggested how the chromophore changes during the activation cycle. Yeah, and this is now our experiment. So what we did is we used PYP, we crystallizes directly on the chips. One of the chips is shown here, and here you see the view through the on-axis. You see this lens-like crystals, which are roughly 15 by 75 micrometers. We opted for an interleaf measurement scan where we scanned in 100 micrometer steps, and then for a second round, moved by 50 micrometer in each direction. We collected at 20 hertz. Here we were mostly limited by the pump laser. We excited at 495 nanometers. This is the pump laser spot, the X-ray laser spot. So we had a nice overlay. Right. And this is the setup, how it looked like at biocars. Here we have our sample holder. We have the X-rays coming from the left. We have the on-axis microscope. We have here a fiber where the pump laser is coupled in, which is then collinear to our sample. Here we have our beam stop. And here's the detector. In this case, we didn't use the rayonics detector from biocars, but we brought a Jungfrau 1M detector. Yeah. Okay, these are just some videos from the data collection. As you see, how the chip is scanned through the on-axis, and this is the on-axis view. Okay, so in the end, we collected some between 200 and 300,000 patterns. We opted for 2 time points. So we took a dark data set, 20 microsecond and 500 microseconds. We roughly had a hit rate of 25%, more or less. For each hit had some of the hits had multiple crystals, so we ended up with many more index patterns than original hits that we had. We could refine the structure to 1.6 angstrom, and with decent refinement parameters. All right, so this is a view of the difference maps, which we got for 20 and 500 microseconds. Blue is the positive peaks at 3 sigma level, and yellow is negative difference density peaks. You see here the chromophore, and you see prominent features in this region, but also in the adjacent region. This region, actually, I will come to this in a second, is part of a symmetry-related molecule, which is basically on this side right underneath the chromophore. So if you look a bit more closely at this, this region corresponds by crystallographic symmetry to this. So here we have the chromophore, right? And we see some difference density signals, but we see also these prominent signals down here, which is likely only coming from a lysine side chain, this is now the refined electron density for the ground state, which has an alternative conformation here, like this is going here, which is not present in the light activated, both light activated states. So that's the reason we have these large features here. But if we just focus on the chromophore, this is the difference electron density, and we see clear pairs of positive and negative electron density next to each other. If you compare this with the proposed scheme of the light cycle, and here I superpose for example, the structure of the PR2 conformation. If you switch back and forth, you see this fits well with part of the positive peaks we have in this region. But if you see here, you have two processes running in parallel. There's also this PR1 state. If you look at the electron density for this, there's actually also some features which might correspond to this PR2 state. So we probably see both states in our electron density maps here. Now looking at the 500 microsecond time point, there's a little less features here, but if you then superpose this PV conformation of the chromophore, this would fit well with the PV conformation. So with this, we think we could show that the analysis or the method itself, the light activation, actually also the downstream analysis, which is running through Crystallography and Pink Indexer, which is also developed in collaboration with the Henry Chapman group, is working quite well. So we tried, now we moved on to a different set of experiments. We wanted, so these light activated states, of course, only work for laser light activated states, only for photoactive proteins. And only a very small subset of proteins is actually photoactive. So if you want to look at protein dynamics and excite your crystals by laser light, you need to look for some other means to activate them. And actually, temperature jump studies have already been done quite a lot for solution scattering, but we here wanted to try this also for crystallography. So the idea is that we hopefully can, if we excite the sample and then can follow in the structure conformation changes, we might decipher how enzyme reaction could occur once the protein is enriched in thermal activation energy. And this should be then generally applicable to all protein crystals. Okay, one of the first proteins we used was also kind of a very standard protein, which is ribonuclease A, which is actually one of the first proteins that was ever crystallized. It depolymerizes ribonucleic acids. Here, there's the deep cleft where it would bind the ribonucleic acid and then hydrolyze it. So we use, for this, we use infrared laser light at 443 nanometers, which excites an OA stretch of water, and the water, the energy which is taken up by the water is then transferred to the protein, and then we follow it by crystallography. So for our experiment, we calculated that the temperature jump should be around 15 Kelvin. So we used a laser pulse of 7 nanosecond, and here for this set of experiment, one X-ray pulse length of 1.5 microseconds, and then the probe delays was simultaneous excitation, and then spanning several decades until 2 milliseconds. So for each of the data sets, they diffracted to 1.7 to 1.9 angstrom. They refined decently. And if you then look at some global parameters, for example, the Wilson bees, kind of the which shows you how the data set is reacting, or the diffraction, overall diffraction is reacting to the infrared laser. We see here at the baseline, this is our laser off, our reference data set, below 15 square angstrom. Then already for the first data point, which is we are at co-laser and X-rays coincide, we have a jump. And then the following time points, this is slowly cooling down or going back to baseline, which we would interpret as a cooling down within milliseconds. We then look at the refined B factors from the structures. We actually see a similar effect, that we have an immediate increase in the B factors, the overall B factors, and which are then cooling down to baseline. We then, of course, can look at the individual B factors for the different time points. And what you should see here, I reference this to the dark state. So the more red it is, the higher the B factors at the particular time point. And what you could see is that overall, you see this cool down, but it appears that we have more increase in temperature factors in the secondary structure elements. However, when we started to look into these FO minus FO difference maps, isomorphous difference map, we couldn't see any clear features. It was rather noisy. All right, this was one of the first experiments we did. We then tried a second experiment. This was now at a different pink beam line at ID09 at the ESRF. Here we had slightly less laser power in a larger spot. So the calculated temperature jump was only about 10 Kelvin. The X-ray pulse are not as bright as at the APS, so we had to use a longer X-ray pulse length too. We used the Jungfrau, and for this particular experiment, we used a tape drive. And we used lysozyme, which is another favorite crystal for protein for method developers, as it's pretty easy to crystallize and reproducible. So here you see the structure of lysozyme with the active site residues. Here again, you have a cleft, where in this case, lysozyme would bind sugar moieties and then hydrolyze it. Like I said, here we didn't use tape chip, but a tape drive. For this, we have a tape which is pulled through the X-ray beam, and then we have a nozzle where we pump our crystal slurry onto the tape. And of course, we have all this liquid still here, which will increase background scattering. And for this, we developed an improved tape drive, which has an integrated blotting mechanism. So what we see here is the top view onto this tape drive. So the tape is pulled from here to here. We have here a nozzle coming in with the capillary, with the crystal slurry, which is deposited here and then pulled across the X-rays, which come here. So this is the on-axis microscope. And then here with these two rolls, we have blotting paper, which is pulled behind the blotting paper, the tape. And the type consists is polycarbonate, which has been etched. So there are sub-micrometer size holes in it. So this is how the installation looked like at ID09. So here you have the perforated tape, and here you have the blotting paper, which is pulled behind it. This was actually done last year after the ESRF EBS upgrade. So what you see here is the spectrum of the X-ray spectrum at the ID09 coming from ID09 undulator. This was in blue the broad spectrum before the upgrade, and in orange the spectrum after the upgrade. And what is important, I will come to that later. So one problem is if you have your crystals, you put your crystals in a Hamilton syringe, and this is then pushing the crystals through this nozzle here onto the tape. But the crystals quickly settle, and then they can start clogging your nozzle. And for this, we have developed, this anti-settling device, which basically you have two syringes, which are set to sit in here, mounted on this rotatable stage. And then we have motorized, we have motors which can push the plunger. So this is a view of the perforated tape. So this is the unblotted stage. You see rather broad distribution of the liquid, while when you blot it, this is much narrower, and you can clearly see now the crystals aligning here at the bottom of this. Of course, now the crystals are prone to drying in, and you need to provide humidified air again, or gas, to prevent them from drying in. This is now how the unblotted and blotted tape looks on the detector, and you can clearly see a much higher background here. If you quantify it or radially average it, you can clearly see the much lower background here. So if you have any weakly deflecting signals in this area, this would be covered by the background here, where you can nicely see them now with the blotted tape. These are just some sample images from the lysozyme crystals we shot. You can see some if you scatter from the polycarbonate tape, but overall this worked pretty nicely. Okay, we collected different time delays, negative time delay, and then up to 2 milliseconds. Hit rate again around 25%. Again, we could multiply index some patterns multiple times. So in the end, we had between 6 and almost 10,000 patterns for each time point. One drawback of the tape is that, of course, if you have your crystals have a certain shape, they might all fall or be blotted on the tape in the same orientation, in a preferred orientation. And this, of course, can be then difficult to cover the whole reciprocal space. And you do see here some tendency, if you plot the reciprocal lattice vectors for the unit cell of lysozyme, A and B are equal. So you see the spheres here, and you can see for the C-axis, you can clearly see some accumulation here. Nevertheless, this was still okay to get complete data sets shown here. So some statistics. This is the correlation coefficient is could be better, but it's okay for the structure. So the structures refined reasonably well. And now here's one thing where we benefited from the much narrower energy bandwidth. And this is that in the pink beam data analysis, it's difficult to detect subtle changes of the unit cell. And when you heat a sample, you would expect that typically the unit cell will swell a bit. But with our experiment which is broad bandwidth, we usually cannot detect this. However, with this smaller bandwidth, it's easier to detect these through the indexing steps. And we could actually fit individual unit cells for this different pump states. So here we see basically our dark state, and then the unit cell is swelling up to 20 microsecond and then cooling down again. The same as for the C-axis. So now if we look then at the B factors again, we see here, let me just go through this quickly, to the overview. We do see the most prominent changes are more here in the periphery. So this is a bit different from what we saw before. But actually, a bit more exciting. So what we then see here again is this is again the relative unit cell change. And if you look again at the B factor change, this more or less coincides with the unit cell changes. So the swelling and the cool down is reflected again also in the B factors. And this is similar to the ribonuclease A example I showed you earlier. But more interestingly, we could also now see some features in the isomorphous FO minus FO difference density maps. Here's just, of course, this is our dark state. We don't see any features here. But then if you look through here, you see for 20 microseconds, we see the most busy difference density map, which then cools down at 2 milliseconds. If you just zoom in onto some regions, for example, here, you see these prominent blobs here, which is actually corresponds to a disulfide bridge, which appears to move up with the heat. And also, if you look here, this corresponds to the active site area. The two active site residues here, we see some pairs difference density, which appear to move in the same direction. So to come to a conclusion at this point, we can, with our fixed target methodology, we think we can follow the local heat distribution of ribonuclease A and lysozyme after the IR laser excitation. We can see more flexible and less flexible regions as judged by changes in V factor. So we could show that the fixed target serial crystallography is working well to detect small changes, like for example PYP, the change in the chromophore. And this in principle makes it also feasible to do sub-microsecond timescale experiment at synchrotrons with the pink beam. For example, at biocars with the 100 picosecond X-ray pulse, and maybe also the picosecond pump laser. Currently, we need probably around 1 hour to 1.5 hours for one time point in terms of data collection time, which is then processed with Crystfell. This time point, so the time it takes to collect one time point can of course be pushed if you use faster detectors, and also accordingly better goniometers, which can cope with these high speeds. And for this, we had developed the goniometer, the Roadrunner goniometer, which has been which we have shown to actually work already at 1 kilohertz. And I don't know if we have maybe 5 more minutes, I can talk a bit more about some more technical developments, Irina, or shall we stop at this point?
I think we can give you another 5 minutes to talk about this. Yeah, okay. That's very important. Yeah, sure.
Right, yeah, thank you. So this is basically our Roadrunner universe. So the goniometer I was talking about is shown here in a technical drawing, which has a very fast scanning axis here. It's completely motorized. We have this on-axis microscope here, which we also use for our experiments at biocars. A capillary mount here, and one of the newest developments is this sample chamber, which is shown here. This is a humidity control chamber. So here we can connect a chiller, and there is the cooling water or whatever you use for cooling is running through the chamber. So you can cool this from -10 to +60 degrees Celsius. And at the same time, we feed in humidified gas, which we can control between 30 and 100 degrees, 100% relative humidity. So in principle, now you can change also the static temperature of your sample and also the relative humidity. And we have developed a control system which is can easily be manipulated through a controller with a touchscreen panel, where you can push in like the set points which you want to, what the vapor, the temperature you want to have, for example, for the humidified air, or the relative humidity you want to have. And then we have humidity sensors inside the shroud reporting on the actual humidity during the data collection. Another thing is that we use mostly silicon-based chips, and this is especially at X-Feld of some concern, because this is monocrystalline silicon, so it also reflects the X-ray beam at certain angles. And if the chip is breaking and the chip is not well aligned, you can have a nasty silicon reflection on the detector and actually destroying the modules. So we also playing with Kapton-based materials, or Kapton material as chip. And here we used UV lithography to etch periodic 5-micron hole pattern into the chip, which is of course probably much more well accepted for you experiments at XFELs. To increase also the throughput, we also working on more automation. For example, we have a hotel for these larger Roadrunner chips where you can put up to 10 chips in. So you can prepare them, blot them, put this cover shown in orange on top. You put them in here, you have humidified gas coming in, so you can keep your samples happy until the beamline is ready. Then you can have a robotic gripper taking the sample from the hotel and mounting it on your goniometer. And the very latest tool we developed is the blotting station, you see here. So because the manually blotting of crystals on these chips can be a source of noise, basically. So you can easily blot these chips too long, and then you have drying of samples. And here, this is normally closed with another lid, so it's completely sealed off. So you would here, there's a lid where you can put your chip in. You could load your sample on there, then you close it. You can stream humidified gas through the whole system. The chip is moving into this position here. You have a touch panel to control it. So the chip is moving in here, shown here, and then we have blotting paper, which can automatically blot from the bottom. And once you're happy with the blotting, the chip can actually move further, because in here there's a magazine with all the chip covers. You can retrieve one of the covers, and then it's sealed. Okay, and this is just a video showing the process, me loading samples onto the chip, right, which is distributed. Then once the chip is ready, it moves into the blotting position. And you have the blotting paper coming from the bottom. You see the liquid vanishing. And you can, of course, observe this and do this multiple times until you're happy with it. As long as you then have humidified gas around it, you don't run into the risk of drying your crystals. Right. Okay. With this, I'm at the end. There are a lot of people which of course have been involved in this. Foremost, Alkemens, who's driving all these projects. Alexandra is still the main force behind processing all this ping data. We of course have a lot of help from the team at BioCast, especially Rob, but also at ID09 from Matteo. Yeah, and with this, I'm at the end and hope you have some questions for me.